Professor Belfrost's science class is back.
Hi, welcome back to my channel, and today we are going to discuss about maybe today I will do a quick revision on the first chapter. We have done our first chapter, right, on unit and measurement. So today we'll review our first chapter as I have promised. Okay, so here I have prepared 8 questions, I think. And here are the problems. The first problem is suppose we are told that the acceleration a of a particle moving with uniform speed v in a circle of radius r is proportional to some power of r and some power of v. So how can you determine the value of n and m? So here's the solution I provided. Please check if I made a mistake or not. So let us take a to be in the expression of a equals k times r to the n times v to the m, where k is the dimensionless constant of proportionality. And by knowing the dimension of each of the term, which is a, r, and v, as k has no dimension, now we can create the dimension equation to be as shown in the slide, and we just need to balance it, okay? And this equation will be balanced under the condition that n plus m equals 1 and minus m equals minus 2, which gives us m equals 2, therefore n equals minus 1. That's why we have the acceleration expression to be a equals k times r to the minus 1 times v squared, which is k times v squared over r. That's it. Second problem, a rectangular plate has a length of this and a width of this. Find the area of the plate and the uncertainty in this calculated area. As we know that area is just the multiplication, the product of length and width. So we just need to multiply the given information, and let's see. We have the result now with us, and please notice that the term zero point 0.2 times zero point 0.1, I dropped it because it will give us a really small value, which is not significant, as we only take a track significant figure, and yeah, that will not be counted. Okay, so at last, after we have finished up the simplified expression, we have our answer, right? Which is 209 plus minus 4 centimeters squared. So where 209 comes from? It is from the product. Okay, this is from the first term. Yeah, the first product. And of course, this is not 209. It will be 208 point something, but because we only have to take we need to take three significant figures as the multiplication. Both of the term gives us with three significant figures, so we need to express it in three significant figures. That's why we run it. Okay, and for the uncertainty, which is 4, yeah, it is 4 if you count it, and it is also rounded. Okay, and that's it. The third problem is here. Antarctica is roughly semicircular. This is the surface area, with a radius of 2,000 kilometers, and the average thickness of the ice cover is 3,000 meters. So how many cubic centimeters of ice does Antarctica contain? So we know that volume of ice is just a product of the surface area, which is in here. In this case, this is semicircular and the thickness. So because we know that the semicircle have an area of 5 times r squared divided by 2, then we have this formula with us. Okay, and we just need to input or substitute all the value that has been given, but please take care because all of the value have different uh, units. Some have the prefix k, some have no prefix, just meter, some have the prefix of centimeter. Then we need to pay attention to what the problem, what the question expects. The question expects to express the result in centimeter. So all of the term we need to change it, convert it into the centimeter. Kilometer to centimeter, the radius gives us 2.0 times 10 to the 8 centimeter, and also the thickness, this is 3,000 figures, and then we need to convert into appropriate value of centimeter, which is 3.0 times 10 to the 5 centimeter, which yields volume equals approximately 1.9 times 10 to the 22 centimeter square, because centimeter cube actually, I'm sorry. uh, but why 1.9? Why we don't express it more? Yeah, as you have noticed, because we have to be consistent about our usage in significant figure. As in before, we have used two significant figures to solve this problem, and till last, we need to stick on that convention. It's very important to be consistent. Number four, problem four. So until 1883, every city and town in the USA kept its own local time. But today, travelers just reset their watches when the time change equal 1 hour. So how far on the average must you travel in degrees of longitude before you need to reset it by 1 hour? Okay, this is a very easy problem. So here's the solution for this. Since we know that a change of longitude equal to 360 degree equals to 24-hour change, then one may expect change of longitude by just dividing these two values, which is 360 degrees divided by 24, which gives us, or which yields 50 degrees, before resetting one's watch by 1.0 hour. Easy, right? Yeah, it's easy. Problem 5. So we so nowadays time standards are based on atomic clocks, and a promising second standard is based on pulsars. Some of these pulsars rotate at a rate as highly stable and sending on a radio beacon that sweeps briefly across Earth once with its rotation like a lighthouse beacon. Okay, so one of the pulsar, it rotates once every blah 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 plus minus 3 milliseconds, where the trailing plus minus 3 indicates uncertainty in the last decimal place. Okay, so please pay attention to this information. This will be very useful when we answer the C question. Okay, so point A, how many rotations does this pulsar make in 7.0 days? B. How much time does the pulsar take to rotate exactly 1 million times? And C. What is the associated uncertainty? So here then. So let us denote the pulsar rotation rate by F, which stands for frequency, and F is given as shown in the slide. So by multiplying the frequency with the time interval, which is given in the problem, 7.0 days, which equals to 604,800 seconds, we ignore the significant figures for this moment, okay, to make it easier to work with this problem. We then can obtain the number of rotations as below. So n equals 1 rotation divided by blah 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 seconds times the t, which is 604 800 seconds, and it gives us 318 rotations, okay, which can be rounded or can be expressed in scientific notations: 3.88 times 10 to the 8 rotations in three significant figures. This is just convention, because why? We use t 7.0 days, we express it 2 in three significant figures. Easy, right? Okay, so now the second one, we want to express the uh, time taken, right? Okay, so we need to know the exact number of pulsar revolution, and we need to know the time it takes to uh, be for the pulsar to rotate 1 million times, right? So here's the formula. We just need to use the previous equation, and we just need to rearrange the terms, and as it's shown in the slide. Okay, so n equals the frequency times t, so t is just n divided by f, very simple, and it gives us this: t equals 1.557 blah 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 times 10 to the trillion. Okay, so if you want to be consistent, you can just express it as 1.56 times 10 to the 3 seconds, as we need to express it in three significant figures too. Okay, so C. Okay, for C, I told you before that you need to pay attention to the sentence that I have underlined before because the problem states that the time uncertainty per revolution is actually not plus minus 3 milliseconds, but it is plus minus 3 relative to the last decimal place, which is 3 times 10 to the minus 14 milliseconds. So we can convert this to be plus minus 3 times 10 to the minus 17 centimeter, centimeter, I'm sorry, seconds, okay? Therefore, we expect that as a result of 1 million revolution, we just need to take the product of these two values, okay? So plus minus 3 times 10 to the minus 17 meter seconds, what I mean, times 1 um 1 times 10 to the 6, and this gives us the uncertainty about 3 times 10 to the minus 11 seconds. I'm sorry, I keep saying my words, okay? Problem 6. Okay, so suppose that while lying on a beach near the equator watching the sunset over a calm ocean, stars stopwatch as the top of the sun disappears, you then stand, elevating your eyes with a height of h equals 1.70 meters, and then start a watch when the top of the sun again disappears. If the elapsed time is t equals 11.1 second, what is the radius of r of Earth? Okay, so in this problem, we need to really sketch. We have urgency to sketch because you cannot just dip in your hand. Okay, this is not just regular calculation. So I provide you the sketch. Yeah, this is a good picture. Your sketch mustn't be as good as this, but you can understand, can comprehend easily. Okay, so please pay attention in it and take a screenshot, take a capture if you find it is necessary. Okay. So when the sun first disappears while lying down, your line of sight, LOS, to the top of the sun is tangent to the Earth's surface at the point A. As you stand, elevating your eyes by height h, then the tangent point will be relative to the Earth's surface at point B. Then we denote d as the distance from point B to your eyes. Then we have this equation. This is just a regular Pythagorean theorem, and we just plug in all the term into the expression, right? So we have d squared plus r squared equals, in bracket, r plus h squared, which gives us r squared plus 2rh plus h squared. And after we solve this expression, we will be remain d squared equal to rh plus h squared. And we know that r is much greater than h, then we can drop the second because it is very small and we square it, it will be smaller. So d squared is approximately 2rh. Now the angle between the two radii to the two tangent point A and B is theta, which is also the angle through which the sun moves about Earth during the time interval t. Then the value of theta can be obtained by using a very simple formula. Actually, I think you have learned it from simple geometric mathematics chapter, which is theta divided by 360 equals t over 24, which gives us, which yields theta equals 0.04625 degree. Or maybe if you want to express it in a more correct significant figures, it must be 0.0463 degrees, right? Three significant figures. Okay. Then using the formula d equals r tan theta, which gives us r equals to h over tan square theta after a very simple algebra. Then by substituting all the value, we have the value 5 times 2 times 10 to the 6 centimeter, which is very great. Okay, we have done with the sixth problem. Here is the seventh problem. Also easy. This is just a very simple problem. Gold has a density of 19.32 gram per centimeter cube. It's the most ductile metal and can be pressed into a thin leaf or drawn on into a long fiber. The problem is, if a center of gold with a mass of 27.63 grams is pressed into a leaf of 1.000 millimeters thickness, what is the area of the leaf? And B, if instead a gold is drawn into a cylindrical fiber of radius 2.50 millimeters, what is the length of the fiber? Here's the solution. So for problem A, you need to take the volume of the leaf to be its area multiplied by thickness. And with the density known and the mass known, then the volume can be found to be as so, which yields 1.430 centimeter cube. And then we need to convert this into the SI units, which give us 1.430 times 10 to the minus 6 meters cube. And because we know that phi equals the area times the thickness, then the area can be calculated, and it yields 1.430 meter square. And the following cylinder is actually very simple too. We just need to plug all the terms to phi equals pi r squared times L. L is the thickness, and we can find the L, the thickness, to be 72.84 kilometers. Very simple. Now number 8, the last problem. So grains of fine California wheat shine are approximately spheres with an average radius of days and are made of silicon dioxide with a density of these kilogram per meter cube. What's the mass of sand grain will have a total surface area equal to surface area of a cube 1 meter on an edge. So the area of each grain is actually very easy, which is 4 times I'm sorry, which is because, yeah, 4 times pi times r squared. The r we need to convert it to meter first from micrometer, and it gives us 3.14 times 10 to the minus 8 meter squared. And we know that the mass of a grain can be found by the formula m equals rho times phi. Phi is the volume of a sphere, and it gives us 1.3610 times 10 to the minus 9 kilograms. We observe that because the has 6 equal faces, then the surface area is 6 times 1 square, which is 6 meters square. And the number of spheres that have this total surface area will be n equals 6 over 3 times 1, 4 times 10 to the minus 8, which gives us 1.91 times 10 to the 8. And it means that the total mass is just the product of this n and the m for each of the grain, right? Which gives us about 0.260 kilograms. Very simple. So here are the exercises for you. They are easy and intermediate problems. I want you to take a screenshot. This is the first slide of the exercise for you. And this is the second slide. I provided the answer for you. So please check your answer. If there is something that doesn't suit, I think, or do you think that there's need to be a correction, please tell me. So here a little inspiration for you. Nelson Mandela once said, "The greatest glory is living lives. I mean, not in never falling, but in rising every time we fall." Great. So this is my lesson for you today. Thanks for watching. Subscribe, give a like, comment, share this video to your friend, and be a good boy and good girl every time. And my class will be on every Thursday and Thursday. So keep watching and be thoughtful. Goodbye. See you all. Love.